Welcome, and today we are going to talk about ultrasonic sensors, how they operate, and the different options that are available. Ultrasonic sensors are a very mature technology and a common way to measure distances or sense an object. They're referred to as ultrasonic sensors because they utilize sounds above our hearing range, usually between 23 and 40 kilohertz. Emitting an ultrasonic chirp, the sensor measures the amount of time it takes for the sound to travel to an object, bounce off of it, and return to the sensor. It is essentially echolocation, much like a bat. We know that the speed of sound in air at room temperature is 343 meters per second, so we simply have to calculate how long it takes for an echo to bounce off an object, multiply it by 343, and divide it by 2 in order to know how far away something is in meters. This may seem like an easy concept, and indeed it is actually quite straightforward. A real ultrasonic sensor, like one of these, is made up of two parts, a transmitter and a receiver, located as closely together as reasonably possible. The transmitter sends out the chirp while the receiver detects the chirp. There also needs to be some sort of logic device that generates the chirp, detects the chirp, and times the echo. Sometimes though, a transmitter and receiver can be combined into a single unit to save PCB space, which is called an ultrasonic transceiver. As you can see from these three options, they look different, but you can't assume which one is which purely on what it looks like. If you happen to have one lying around, when in doubt, look up the datasheet to confirm what type of ultrasonic sensor you have. There are some real-life considerations to think about with an ultrasonic sensor. First, when the noise comes out of the transmitter, it doesn't leave straight like a laser, but spreads out in a cone shape. The size of this cone is dependent on the beam angle, and it varies between sensors. In general, a narrow beam angle is more selective and has a longer range, while a wide beam spreads the energy in a wider arc. The beam angle isn't necessarily a better or worse factor, simply one that needs to be chosen based on the needs of your application. Narrow beams may avoid false positives by limiting the detection area and increasing the range, while wider beams can cover larger areas and reduce the number of sensors needed to cover the same area. Being such a mature technology, not only is it reliable, but the benefits and drawbacks of ultrasonic sensors are well documented. They are unaffected by color and lighting, making them work extremely well in varying lighting conditions or with translucent or transparent objects such as water or glass. They are relatively precise with a typical precision of about 1%, though more precision can be achieved with both special sensors and a controlled environment. Taking into account beam spread, ultrasonic sensor minimum and maximum ranges are surprisingly wide, with most sensors able to detect as near as a few centimeters up to around 5 meters, though there are models that go up to 18 meters. Even at that maximum range, the time it takes the acoustic pulse to travel to the target and back is quick enough that the refresh rates of ultrasonic sensors are fast enough for most purposes. Finally, ultrasonic sensors are resistant to both electrically and acoustically noisy environments, particularly when using modules that encode the chirps. Like everything, there are trade-offs here as well. The speed of sound is dependent on temperature and humidity, so environmental conditions may change the precision of the measurements. However, this tends to be inconsequential in all but the harshest of environments or with the strictest of demands on precision. And even though the detection zone is three-dimensional, an ultrasonic sensor only detects that there is an object a certain distance from the detector and cannot provide feedback on where the object is in the sensing area, nor any features such as shape or color. And while these sensors are relatively small for industrial or automotive applications, you can see that they would be too big for very small embedded projects. And while this may not affect most of us, these do need a medium for the chirp to pass through, so they do not work in a vacuum. With these considerations in mind, it's easy to see that ultrasonic sensors would still be the ideal solution for a large variety of applications. They remain a staple in modern industrial applications and liquid-level sensing, but are becoming more and more common on vehicles as well. Even hobbyist robots are rarely seen without an ultrasonic sensor anymore. Unlike other technologies that seem to come and go, the demand for ultrasonic sensors continues to climb with no end in sight. If you have any questions or want to learn more about the different sensing options available, check out our sensors blogs on cuidevices.com.